With just over $1.5 billion, China has dealt a devastating blow to the Western energy empire, turning the tables with one of the most ordinary salts on Earth. While American tycoons continue frantically digging into the ground in search of lithium, a design abandoned back in the 1960s has been revived and transformed into an energy storage machine that pushes beyond conventional limits. It is virtually non-flammable, can charge to 80% in just 15 minutes, and can still deliver power in deadly cold as low as -58 degrees Celsius. With a massive 60 gigawatt-hour contract now secured, lithium's once unshakable throne has begun to crack. Join Mandarin Tech as we explore how China revives sodium-ion batteries to reshape the future of global energy. Over the past 30 years, more than $1 trillion has been poured by the United States and Europe into the race to secure lithium, the so-called white gold. From digging across the vast salt flats of South America's lithium triangle to exploiting barren hard rock mines in Western Australia, a fierce geopolitical battle has taken shape over every gram of this mineral. Caught in this race, industrial giants such as Tesla, Panasonic, and LG Energy Solution came to assume that the energy storage game had already been decided. They chose to keep expanding existing production lines rather than step outside their comfort zones in search of new solutions. But the reality of the market was far more fragile than it appeared. In just 24 months, the price of the core material behind this empire once surged eightfold, only to lose 70% of its value the following year. The entire foundation of humanity's green energy transition was being placed on a wild price roller coaster. What you are about to witness is not a futuristic miracle. It is a cold, hard business case study. One in which the complacency of industry leaders accidentally created a fatal opening, paving the way for one of the most dramatic upsets of the modern era. Let's turn back the clock to the early 1990s, when mobile phones were as big and heavy as bricks. Laptops were bulky blocks of plastic, and a video camera could drain its battery after barely an hour of recording. The idea of a thin, lightweight device that could fit in your pocket yet keep running throughout an entire day sounded more like science fiction. At the time, every attempt to pack more power into a smaller space ran into one brutal physical barrier: weight. Then came 1991. Sony introduced the first commercial lithium-ion battery, and the world changed forever. The amount of energy that could be packed into each kilogram of battery suddenly increased by around 3 times. The transformation happened almost overnight. Suddenly, everything began to shrink. Wireless earbuds appeared in people's ears, millions of ultra-thin laptops filled coffee shops, and electric cars finally began rolling on real roads instead of dying on engineering blueprints. We are living in an era shaped by that very breakthrough. Why did lithium become so successful? The answer lies in 2 powerful advantages given by nature. First, its atomic structure is extremely light. Millions of these tiny particles can be packed into a small space without adding much weight to the device. Second, this metal has an exceptional ability to drive a strong electric current through a circuit, outperforming most other elements found on Earth. Lightweight and powerful, it was the perfect formula. Lithium quickly rose to the throne, becoming the absolute king that powered the heartbeat of an entire planet. When an industry becomes consumed by profits, complacency begins to set in. The tech world stayed busy expanding production while ignoring 2 physical weak points that had been warned about for years. The first was thermal runaway. The Samsung Galaxy Note 7 disaster in 2016 became the clearest and most expensive example. 2.5 million devices were urgently recalled, wiping out around $5.3 billion. The core problem lay in the organic electrolyte inside lithium batteries. When temperatures rise beyond roughly 60 degrees Celsius to 130 degrees Celsius, this liquid can ignite. Once the first cell explodes, heat can spread to neighboring cells within milliseconds, triggering a chain reaction that no cooling system can stop in time. The second weakness appears in extreme cold. At 0 degrees Celsius, lithium ions already begin to move more slowly. By -20 degrees Celsius, usable capacity drops sharply. According to data from the American Automobile Association, cold weather combined with cabin heating can reduce an electric vehicle's driving range by as much as 41%. Even worse, charging a battery below freezing can trigger the growth of sharp, needle-like crystals known as dendrites. These can pierce the insulating separator, cause a short circuit, and ignite a fire from inside the battery. Automakers have spent billions of dollars strengthening battery management systems, or BMs, and adding bulky cooling systems. But these solutions are only bandages covering a deeper limitation. Lithium performs poorly in the cold and always carries the risk of catching fire. As the market's patience began to wear thin, an opportunity opened for a technology that had been forgotten for half a century. There is an ironic truth that the Western tech world rarely talks about. The challenger to lithium's throne had actually appeared long before the current king ever rose to power. On the periodic table, sodium sits quietly just below lithium. The two share a similar basic structure, but sodium holds one crucial advantage: abundance on an almost unlimited scale. It is dissolved throughout the world's oceans, found beneath the ground, and can be extracted at extremely low cost. Few people realize that sodium was actually one of humanity's earliest starting points in battery development. In 1966, Ford introduced a prototype sodium battery. But in practice, it was a nightmare. To keep the charged particles moving, the battery had to be continuously heated to around 300 degrees Celsius, hot enough to melt lead. Putting a blazing furnace like that beneath a family car was simply impossible. This dead end was broken in 1972, when scientist Stanley Whittingham found a way to make lithium work effectively at room temperature. That single microscopic breakthrough immediately changed the course of history. Trillions of dollars began pouring into mining operations around the world. Lithium raced ahead and eventually claimed the throne almost entirely for itself. Meanwhile, sodium was thrown into the research trash bin for nearly 40 years. Not because it was an inferior material, but because investors were unwilling to risk their profits trying to solve a physical problem that seemed to have reached a dead end. And that brutal problem came from something incredibly basic: the natural size of the atoms themselves. Sodium's core problem was simple but deadly. Its atoms are about 35% larger than lithium's. Inside a battery, charged particles must repeatedly move in and out of a storage structure, usually graphite. Lithium is small enough to slip through easily. Sodium is not. Each time these oversized ions force their way in, they damage the graphite structure. After only a few hundred charging cycles, the framework begins to collapse. Energy may still remain, but the battery is effectively dead. A possible solution appeared around 2000 with an unusual material from Canada called hard carbon. If graphite is arranged neatly like a deck of cards, hard carbon is the opposite: a frozen mess full of irregular gaps, pores, and cavities. Yet that disorder became its greatest advantage. Those empty spaces provided enough room for large sodium ions to move in and out without tearing the structure apart. A problem that had lasted for decades suddenly seemed solvable. But the solution came with a serious weakness. Hard carbon is extremely sensitive to moisture. Even tiny amounts of water entering the cell can trigger chemical reactions that produce gas, causing the battery to swell and potentially fail from within. Controlling moisture in a laboratory is easy. Doing it across an industrial production line, making millions of cells, is another matter entirely. The cost was enormous, and few American companies wanted to take the risk. So the research was pushed back into the drawer, where it gathered dust for another 20 years, waiting for a player bold enough to take the gamble. In reality, even a great invention can remain nothing more than a piece of paper if it cannot survive the manufacturing valley of death. The West stepped back from sodium because of two brutal engineering barriers. The first was economic: drying costs. Hard carbon naturally absorbs moisture, which meant a gigafactory would need an ultra-clean, extremely dry production environment covering a massive area. The electricity bill alone could quickly wipe out sodium's cost advantage. The second was precision. Producing billions of structures with nanometer-level accuracy on high-speed assembly lines seemed almost impossible. If the pores were too small, sodium ions would get trapped. If they were too large, energy density would collapse. Wall Street rejected the risk and effectively sealed the project. America walked away. But in Fujian, China, battery giant CATL chose to overturn the table. For nearly a decade, the company quietly poured $1.5 billion into the technology, patiently fixing the weaknesses its rivals had dismissed. Its solutions were brutally practical. If drying an entire factory was too expensive, CATL attacked the material itself. Engineers coated the surface of hard carbon with a molecular raincoat, helping repel moisture and reduce the risk of swelling from the start. Then they spent heavily refining pore size, turning hard carbon's chaotic internal structure into millions of more uniform storage sites, carefully matched to the larger sodium ions. Through persistence and a billion-dollar gamble, CATL broke through the final physical barrier, pulled sodium-ion batteries out of the laboratory, and pushed them directly onto commercial production lines. The faint glow of the sterile laboratory was left behind. When the first Naxtra battery rolled off CATL's commercial production line, it was more than metal and chemicals. It was a direct challenge to years of industrial stagnation. First came speed. The battery could charge to 80% in just 15 minutes, about the time it takes to stop for a cup of coffee. Then came durability. With more than 10,000 charging cycles, Naxtra could last around 27 years if charged every day. In other words, the steel body of a car could rust away and be recycled twice before its sodium battery finally stopped working. But its most impressive performance appeared in extreme cold. At minus 58 degrees Celsius, the electrolyte could still function. Even at minus 40 degrees Celsius, when lithium batteries struggle badly, Naxtra could retain up to 90% of its capacity without relying on bulky extra heating systems. Then came the final blow: cost. CATL reportedly pushed production costs down to about $19 per kilowatt hour, while lithium batteries were still costing Western automakers roughly $55 to $70 per kilowatt hour. A battery that promised greater safety, longer life, and far better cold weather performance could cost only a fraction as much. That helps explain the massive 60 gigawatt-hour storage contract that was quickly secured, an order equal to nearly half of what the company had sold worldwide the year before. The doubt was over. Sodium-ion technology had finally escaped the laboratory and entered the real world. But don't rush to throw away the lithium battery inside your smartphone. Despite its low cost and outstanding durability, sodium still faces one unavoidable physical limit: energy density. A sodium atom is about 3 times heavier than lithium. This bigger, heavier element will never be ideal for a 7mm thin smartphone or high-performance sports cars obsessed with cutting every possible kilogram. The real gold mine, however, lies in the mass market. The first battlefield is affordable electric vehicles. By cutting battery pack production costs by around 30%, sodium could narrow the price gap between EVs and gasoline cars, powering millions of vehicles expected to fill the roads over the next decade. But the biggest opportunity is the national power grid. Instead of building enormous, expensive lithium powder kegs near cities, stationary energy storage systems mainly need 2 things: low cost and safety. If the battery system is the size of a shipping container, it hardly matters. Sodium storage stations covering an area as large as 5 football fields could operate quietly in scorching deserts or frozen highlands without requiring billion-dollar cooling systems. Sodium will not completely replace lithium. Instead, it could capture the largest and most profitable mass-market segments, forcing the former king to retreat into a much narrower space dominated by premium applications where high energy density still matters. The 60 gigawatt-hour contract is more than a commercial agreement. It is a death sentence for Western complacency. America had sodium battery designs in its hands as early as 1966, but the promise of quick profits from lithium blinded the industry. Silicon Valley and Detroit became trapped in the innovator's dilemma, ignoring obvious weaknesses and refusing to rock the boat while the money kept flowing. The result is an embarrassing geopolitical tragedy. Right now, tens of billions of dollars in American and European taxpayer money are still being poured into massive lithium gigafactories. They are racing to pour concrete, build production lines, and cut ribbons for a future that their rival may already be moving beyond. New energy storage projects in the West could still remain more expensive, have shorter lifespans, and carry fire risks that Chinese manufacturers claim to have reduced through newer sodium-ion designs. While the West continues digging across South America in search of scarce minerals, China has quietly rewritten the rules. It did not search for another gold mine. It turned an abundant, low-cost material found across the world into a potential weapon of disruption. The energy battle of the 21st century has entered a new chapter. It is no longer decided simply by which country can extract more minerals from the ground. It increasingly belongs to whoever controls the core technology. For the first time in 3 decades, the world may have a real alternative to lithium dominance. And for the United States, the bitter reality is that the key to this new era may no longer be in its hands. The era of every monopoly eventually ends with an unexpected overthrow. Sodium-ion batteries are more than a breakthrough in chemistry. They are a harsh reminder from the business world. The future belongs to those willing to leave their comfort zones and break old limits. So, if tomorrow an electric car powered by salt appeared, significantly cheaper, still reliable in brutal winter conditions, and far safer from fire risks, would you be ready to drive it? Leave your answer in the comments below. If today's story gave you a sharper view of the global technology race, don't forget to like and subscribe to Mandarin Tech. See you in the next journey.